Welcome, class. We're going to go through the last little section on this section on trig, and we're going to discuss hyperbolic trigonometry and what these actually come out to look like. Remember that trigonometry works in the idea of the Euclidean sense. Hyperbolic is basically used for everything in the real world, but because things don't quite work out. So let's talk about it. So first we're going to talk about hyperbolas and ellipses. So oval isn't really a well-defined term. Eggs are oval, but eggs are thicker at the bottom than they are at the top, but they're still oval. So that's really not a good term. Where an ellipse is a symmetrical shape, meaning it's the same at a top as it is at the bottom, or on the sides, each side is the same. So it's symmetrical, so that's important. Circle, we'll go back to the definition of a circle. The set of points in a plane such that the distance from a fixed point, the center, is constant. This means it's kind of like the ring, right? That's kind of how I talked about it in class. It's like the ring, it's the outside. It's every point on the outside. It's not the inside. That's going to hold true with the ellipse. So the ellipse is a set of points in a plane such that the sum of the distances from two fixed points we call foci is constant. Foci is plural of focus. Like cactus is plural of cacti. So same idea. The other way around. Let's try that again. The other way around. All right. So we have 2 points, and those two fixed points, the sum of the distances from there is how we will define the ellipse. That constant distance 2r is defined such that 2r is greater than the distance between the foci. So that they're going to kind of be something like, and we'll have a focus here and a focus here. And when we're defining it, we're saying that any particular point, say here, these points, the sum of this distance from here to here added together is going to be constant no matter where I am. So if I'm over here, it will be the same value as that distance. So this, and this, and this, and this, summed up must be the same value. So the one with a single mark plus the one with the 2 marks must be equal to the one with 3 marks plus the one with 4 marks. And that moves, right? Like these points move. I could have chosen over here. I could have actually chosen over here, or over here. The idea is that the distance from each one of these must sum up to be the same, and that's the definition of an ellipse. We also know that the constant distance 2r is defined such that 2r is greater than this distance, this dashed line between the 2 points. 2r must be greater than that. All right. Oh, here's a much better picture. Okay. So we have our focuses here and here, and we can talk about this distance as it moves around, but it'll always be constant. The segment from center to vertex, that's here. So over here we have this from here to a vertex, and it really doesn't matter which one, is called the semi-major axis. It's half the major axis. So from here to here is a semi-major axis. It's half of the axis. And then we have from here to here, and that's semi-minor. They're not crazy, just how we define them, right? So that's a semi-minor. If we're talking about the whole thing, so this whole thing, well, that's the minor axis, and we talk about this whole thing all the way to there. That is our major axis. So when we talk about ellipse, there is a minor axis and a major axis, and those will help us write a formula, or not really a formula, an equation that would tell us we have an ellipse. My hope is you guys are comfortable with the idea that there's an equation that says you have a circle, right? And that's the one that's in basic terms, it's this idea: x squared plus y squared equals some r squared, right? And that's a circle. Like, we know that's a circle. Let's see how we get an equation of an ellipse. So whatever the distance is for our focuses, we have one focus here, and then we have the negative on the x, right? It's the negative version. They should be equal from the center, whatever that center may be. Now here we're going to talk about it on the xy plane, and we're going to put the center at the origin, but it isn't always there, right? This could move just like this circle could be shifted left, right. It doesn't have to be on the origin. This particular one is, but when it's shifted, it looks a little different. So same idea. So let's see what we can do here. So we know that the distance to any particular point, doesn't really matter where, on our ellipse is going to equal the distance to x naught, y naught, and plus the distance to x1, y1. So this distance, say from here to, I don't know, here, and from here to here, right? That's equal to 2r, and that's going to be constant all the way around the thing. For the foci on the x-axis, center at the origin, as I said, we have this. This is actually the formula. And this is kind of like making a unit ellipse. Well, not kind of. It is making a unit ellipse. Just like a unit circle where the distance is 1, this is the same idea. We're making a unit ellipse. And we have x squared over r squared plus y squared over r squared minus f squared. Now, this piece works here because really the f's are the same when we're centered at the origin, right? So this is important. We have to be centered at the origin for this to work. Because this is going to just be, if it was negative and we squared it, it'd still be positive. If it's positive and we squared it, it's still positive. So we don't really need to worry about it. It does need to be centered at the origin. Technically, it does need to be on the x, which would make it on the x-axis. So I feel like that's kind of maybe even redundant, but it does need to be both of those things. So we have our first piece of an equation, but that's for a specific one, right? So then we have to say, well, okay, let's think about it. This is determined by the focus and the radius, where f's just a positive real number greater than 0, right? The focus isn't the origin. Since we're centered at the origin, that would be really, would be impossible is what it would be. It would no longer be an ellipse at that point. So This is what we have. And these are the general rules, right, which determined by those two. And we have that f's a real number. All right. Now, the major axis horizontal centered at the origin. So this is where we have from the origin to our A and negative A, and our origin to B and negative B. Could be written like this. This is a major axis horizontal. So this is the same idea. This is just another way to write an equation of an ellipse. But in this case, our A squared is going to equal whatever that is, whatever the outside is. And it doesn't matter. We're centered at the origin. This again has to be centered at the origin. But if we don't know the focus, say I don't know what this is, and I don't even know what R is, I can use this, because this number here, or the square root of that number, should be a positive and negative version of my x values. And this number, whatever that comes out to be, that the square root of b, is the positive and negative of our minor axis. So those are the y values of our minor axis. This is the x values of my major axis. And in this case, obviously, because, well, maybe not obviously, and I hate saying that. I hate saying, well, you all know, I don't like obviously. But it should make sense that this A, because it's on the major axis, is bigger than the B that's on the minor axis. Can an ellipse be tipped the other way? Can an ellipse go this way? Absolutely it can. It can. But to do that, we basically shift everything, so we're rotating this one this way or this way. It's really the same thing as if it's laying horizontal. We just rotate it by 90. But if it's not rotated, you expect, and that's how we're dealing with this, is we expect this piece to be greater than this piece, because this would be the major axis and this would be the minor axis. And I mentioned the vertices, and that the length is 2a. I didn't actually mention that, but because this is a distance from the origin, and we are centered at the origin again, then it must be that the major axis is 2 of those. This distance from here to here, the semi-major, which would be a, plus the semi-major for this side, which would also be a, so 2a. And I guess I should say this would be b for the semi-minor and b for the semi-minor, so 2b on the vertical, or the minor axis. And then same thing. Okay. The focus, we're just going to put it at C and negative C, and it holds that this piece would be true. Because we didn't know the focus, but we knew A and B from our equation here. We would also know that our C squared, so the distance from here, this distance squared, should equal all of A squared, so the distance from here to here squared, minus the distance from here to here squared. And that would be our from the center to our focus. So this gives us a couple of equations. We have this one we started with, right, centered at the origin. We have this one, and then we also have this property about our center. But if we really look at these, then our r squared is equivalent to our a squared. So r is equivalent to a. And this then is a here. And we're minusing this here. So what would I have to do to this to get it in terms of b? I would add b to both sides. Maybe let's do that real quick. So I would add b squared, so b squared, and then minus c squared. Why don't we just minus the c squared right now? C squared and minus the c squared. So b squared is equal to a squared minus c squared. And this piece here, so this is b squared, and all of this is equal to it. Well, then I can just replace this with what I have here. I knew that that was a squared, so f squared must be equal to c squared. So we have that c equals f. So these are some properties that we have when we compare these equations, and a lot of it depends on what you're given. You're usually given it like this, but oftentimes they'll give it to you like that and ask for your radius or for your r and your f. But knowing how this equation moves to become this equation, using this equation to get there, will give you these properties, which can be useful. Hyperbolas, that's another process that happens, and we'll talk about how they're a little bit different than an ellipse. The set of points in a plane such that the absolute value of the difference of the distances from the two fixed points is constant, or the difference of the distances from the two foci is plus or minus 2r. And did I have a picture? I did. Great. So again, they can go different directions. So I have a transverse axis is here, this little piece, or here, depending upon the direction that we're going. And you'll notice the focus here. In these cases, these are on the XY with the center, and the focuses just move either on the X, they're either on the X in this case, or on the Y, depending upon the direction that we have. And we have an equation for our hyperbola. So again, using this idea, the distance to a particular point minus the distance to a particular point. So again, we have a minus, and that's kind of how you tell the difference between an ellipse and a which one will be which in hyperbolic trig and in hyperbolic geometry. We look at, does it have a minus or does it have a plus? Plus is going to be an ellipse, minus is going to be a hyperbola, and then it's equal to plus or minus 2r. Focus on the x-axis, center on the origin, gives us this equation. And yes, it is really, really close. Again, center at the origin. What do we know that's different? These are reversed for one, right? That's something. What else is reversed? Or what else is different? Yep. All right, and kind of take you back. Oh no, my writing stays. Oh no, it does go, okay. Nope, stays a little bit. Oops, I wanted to go to here. And you can kind of see, here we have the plus, and it's r minus f. Going back to it, put everything in. Come on. There we go. And here it's a minus, and it's f minus r. And it's determined by the foci and the radius, just the same as the other one was, or the foci and the r. I keep wanting to call it radius, but we're really not. It's not a radius. They should have probably came up with a different letter for that. The transverse horizontal, centered at the origin, does have this same equation, except it's minus, right? Same as the previous one, except minus. And this is what we're looking at. The hyperbola, either a or b can be greater, right? Sure. A's here. A is just the denominator in the positive term. That's all it is. So this A is just the denominator. It does tell us where the vertices are, where the shifting happens, because a vertice means a change in direction. So we really do change direction at that point. It has a length of 2a. So the distance from here to here, and 2a is from here to here, right? So the transverse axis has a length of 2a. It goes all the way. The focus, we have c, and negative c, and this distance from the center to the focus can be given by the Pythagorean theorem, if you want to think of it that way, even though we're not thinking of it in that term or in that direction. It totally does work. It is c squared is equal to a squared plus b squared. So this distance squared is equal to this distance squared plus, and it's actually, instead of thinking of it, it is this distance squared, but it's really this denominator and this denominator. Your b, which I have drawn in here, it was not in here, but we would put it somewhere. Well, actually where it goes. It forms a box, is what it does. And the box is formed by this line. It's not necessarily, oh man, that's horrible. Not necessarily square, it can be rectangle. But what happens is its diagonals, and that's not right, that's a horrible drawing, becomes these asymptotes that your hyperbola never actually hits. So they're like slant asymptotes, but you have two of them, which is kind of weird. When you guys are used to asymptotes when you think about rational functions, and there are slant ones, but to have two slants going opposite directions would feel kind of weird. So this is this imaginary box around the center. It's really not there. I want to be clear, it's really not there. And the asymptotes pass through the center of the box and the corners of this imaginary box. And what's I think is kind of cool, I don't know. You guys may or may not. So B, remember the equation. The equation is x squared a squared minus y squared b squared, right, is equal to 1. So a and b are your slopes. So b over a is one of them, and then the other one is negative b over a. Those are your two slopes. And when we talk about an equation of these lines, it's basically y and this one in here, and then this one in there. So that is how we draw them. We need those horizontal asymptotes to know where we have to cut off. We do have right hyperbolas, They're not always right. So this isn't necessarily right here. It doesn't always make a right angle where they intersect. They are not always, these slopes are not always negative reciprocals. You'll notice this one doesn't look like a negative reciprocal of each other. Sometimes they are negative reciprocals of each other, and then we get what we call right hyperbolas. And they're written, well, basically like this. So this is a hyperbola whose asymptotes meet at right angles. They're called right hyperbolas. And this occurs when f is equal to the radius times the square root of 2. Or not the radius. F is equal to r times the square root of 2. Oops. And they're just a more specific hyperbola. All right, let's talk about some trig functions with hyperbolic geometry. So we have our trig functions. I'm hoping you guys are pretty comfortable with those, and we'll kind of talk about where they're related. The trig functions were used to find points where x and y terminal sides of an angle intersect a unit circle. And the unit circle has this property: x squared plus y squared is equal to 1. So we should be able to do the same thing with any curve, albeit some curves don't look like real nice, and their equations or their properties, their functions, wouldn't also. So we don't do it with every curve, but we do it with hyperbolic. One of the reasons is because hyperbolic is how things want to come to rest. If you took a string and held it between your hands, and just gave it just a little bit of slack, it will always form a hyperbolic curve. It's not going to form a circle or even a part of a trig curve without you manually making it that way. They just don't do that. Now, the tension and vibration of a spring could be modeled with trigonometry, but just letting it rest, it's going to almost always turn into a hyperbolic type curve. So let's see what we have. So first, let's think about what's happening. If we talk about the xy terminal side angles, right hand branch of a hyperbola, so we're only focused on the right side here, right? We're not focused on the left side. And this is the equation, again, very similar to the circle, but not quite. We have that sine of h is equal to, or sine of theta, sine h of theta, is equal to y, so the y value. Cosine is equal to the cosine h of theta is equal to the x value. Well, we know from our trig that sine of theta is equal to my y value, and cosine of theta is equal to my x value. So that's true. Nothing changes there. In fact, you're going to find that most of these don't change. When we talk about tan h of theta, it is y over x, sine over cosine. Well, that's really what tangent is, right? It's y over x. So tangent of theta is just equal to y over x. Same thing. These all hold the same thing. Secant h of theta is 1 over x. And we might think of that as secant of theta is actually equal to 1 over sine. 1 over cosine of theta, which would be 1 over x, right? And cosecant h of theta is 1 over 1 over y, and cosecant of theta is equal to 1 over sine of theta, which is equal to 1 over y. And then cotangent h of theta is the opposite of tangent, or the reverse, so it's x over y. Oh, wait, I put that wrong. This should be x over y. My bad. That's a typo. Dang it. Okay. So it's x over y, just like cotangent of theta is equal to 1 over tan of theta, which is equal to cosine over sine, or x over y. Same idea is holding true. And remember, we're looking at the side of this angle. This is our theta right there as it moves, and it's actually the point here that hits that we would then find. When we used these two, it would give us our xy point, but we could talk about tangent of that and secant and everything else. So same stuff's holding true from our trig stuff. We also have some the graphs. You'll see how the graphs look. So sine of x is this one. This is our regular trig function. And sine h of x is just doing that. It's more like a cubic function. And before, tangent of x was like this, right? But tan h of x is more like a cube root of something. Kind of looks like more like a cube root of something. Cosine does this, and cosine h does this. Okay, so they are different. They do make different graphs. They do connect. So in each case, you're going to find a particular point where these hit. There is always a point where they hit. So that's kind of interesting, where the two are equal at that particular value. It's not always the origin. I do see that it's the origin. I do know that it's the origin here and with tangent, but it isn't always, as you can see here with cosine. And it's not always with any of the. They do all touch at some point, but they're not always at the same particular point. The basic identity of hyperbolic trig, so, is this, and this may look very Pythagorean without being a Pythagorean theorem. It is Pythagorean type look, because just like the Pythagorean identities, you can derive the others by dividing sine h squared or cosine h squared of theta. And in trig, the Pythagorean identity is the sine squared of theta plus cosine squared of theta is equal to 1. Right? And you can get the other three by dividing by sine squared or dividing by cosine squared, and you get the other three identities. Same process is held true with this, so you can derive them. Maybe, I don't know. All right, maybe derive one of them just so you guys see how it's done. I kind of am taking for granted that you guys all know this, but maybe you don't. So let's just be clear. When I say that, maybe I should have done it with the trig ones just for, well, it doesn't matter. All right, so I'm going to divide them by sine h squared of theta, and I'm dividing this by sine h squared of theta, and this, right? Divide everything by the same thing. No hokey math here. This becomes 1. That's beautiful. So we have 1 minus, well, cosine over sine is cotangent squared of theta is equal to 1 over sine is, which one is that? That is cosecant. Cosecant h squared of theta. And this is the other identity. And then you could have divided this whole thing again by cosine squared, and you would get a different property. You would get tangent minus 1 is equal to secant. So yeah, great opportunity to practice these. We will go right into the homework exercises, so my hope is you will have a chance to watch this. All right, have a good day.